Alright, I want to take a look at the graph of y equals the tangent of x. I'm going to do this by thinking about it in terms of the sine of x divided by the cosine of x. Okay. And the reason I do this is because I know about sine and cosine. And I'm thinking in terms of rational functions where the numerator tells me about x-intercepts, the denominator tells me about vertical asymptotes, right? Whenever the numerator is equal to 0, the whole function is equal to 0. Whenever the denominator is equal to 0 is where the function's undefined. So I'm going to look at several graphs here. How about in red? No, how about in blue? I'll do y equals sine x. So here we go. And this is my standard sine curve. From 0 to 2 pi is one cycle, so that was back to minus 2 pi here. Right, intercepts at pi and minus pi, and all the integers times pi. So 0 times pi, 1 times pi, 2 times pi, and so on. 3 times pi, negative 1 times pi. So that's y equals sine x. In green, let's do y equals cosine x. Cosine starts here at 1, goes down to 0, down to minus 1, back to 0, back to 1, and then repeats itself in both directions here. Right. Okay, so I can look at these two graphs and say, let's do the tangent in red here, y equals tan x. Whenever the sine, the numerator is equal to 0, so is the tangent. So the tangent is going to be 0 right here, right here, right here, right here. Every place the sine is equal to 0, the tangent is equal to 0, because sine is the numerator. Every place the denominator is equal to 0, so when is the cosine equal to 0? That's where the tangent is going to have vertical asymptotes. So there, and here, and these happen to be on the pi over 2's, the odd pi over 2's. So this one's right here at 1 pi over 2, and then this one's at 3 pi over 2, and 5 pi over 2 right there, and minus pi over 2 back here, and minus 3 pi over 2, right? That's where the cosine's equal to 0. That's where the tangent has vertical asymptotes. Okay. Now I look in between what's going on. Well, let's look here for angles between 0 and pi over 2. So first quadrant angles. Both the sine and the cosine are positive. So when I look at this fraction, a positive number divided by a positive number is going to be positive. So it's going to be headed up like this. And as the cosine is getting close to 0, and the sine's heading close to 1, 1 divided by a really small number is getting really big. Okay. Likewise likewise. Over here, we have one of them positive and one of them negative, and so the quotient will be negative, and we're going to be headed down to the asymptote like that. Right? When one is positive and one is negative, the quotient will be negative. When they're both positive like here, or both negative like here, the quotient will again be positive. And so we'll end up looking like this. A couple of things to point out here. When you're at pi over 4 is a spot where the cosine and the sine cross each other. So when you look at that quotient, numerator and denominator are the same thing, and so the value of the tangent at pi over 4 is actually 1. When I think about sine and cosine, they have amplitude 1. Apparently I didn't draw this accurately enough, but sine and cosine have amplitude 1, so that's why they should be all at the same height. But that's an interesting point to me. One thing I notice as well is that the tangent repeats itself not in 2 pi, but it repeats itself every pi. Either you think of it between minus pi over 2 and plus pi over 2, there's that one section there that then repeats again over here and repeats again over there. Or some people think of it repeats between 0 and pi. So there's that, which then repeats again right here. There we go. And then repeats again, right? So the period here is pi. The asymptotes are on the odd pi over 2's. The intercepts are on the even pi over 2's. going to give you a little cleaner graph of that. Let me switch over to the graphing calculator here on my iPad. So what I've got right now is a graph of the sine curve. Notice the period here is just a little bit bigger than 6, so there's your 2 pi. I'm going to add in the cosine of x. Save that. Take a look at the graph. Okay, so now in green is the cosine curve, starting at 1, 0, minus 1, 0, up to 1. By the time that sine did 1 complete cycle, the cosine also did, right? So the period is 2 pi. And now let's add in the tangent. Tangent of x. Save that and draw the graph. And there we go. I find it interesting that once the tangent comes in, it changes the grid. Notice that where this is up at 2, so each square here seems to be worth a half. 1/2, 1, 1.5, 2. In this direction, each is worth pi over 6. 1 pi over 6, 2, 3, 4, 5 pi over 6. There's 6 pi over 6 is pi. That is that first cycle of the tangent ends right at pi there. So this is scaled in a little bit this way because pi is a little bigger than 6. So this should be stretched a little bit. Rather than having squares here, they should be a little bit rectangular. But anyway, the point is the tangent and the sine cross the x-axis in the same places, right? The cosine crosses the x-axis when the tangent has an asymptote. Every time the cosine crosses, the tangent has an x-asymptote. One more thing to point out. If you look at the sine and the tangent as they pass through the origin here, they both pass through the origin with slope 1. So just as you draw on the graph, you get an idea of how steep to make it. The tangent has slope 1 as it passes through the origin. In fact, every time it passes through the x-axis, the slope is 1. Okay. Anyway, there's the graph of the tangent.